Hello and welcome to our lecture on ensemble methods in machine learning. I am Dr. Andrei Holz, and today we will discuss the mechanics and practical applications of ensemble techniques. Ensembles, such as bagging, boosting, and stacking, are not just about combining models, they are about using the strength of multiple models to create unified, powerful solution. Ensemble methods are great at handling complex, noisy datasets and often outperform individual models in accuracy and robustness. Let us get started. Today we will cover bias-variance trade-off and why this is important for choosing and tuning models. We will have an introduction to ensemble models, the basics of how ensemble methods operate. Then we'll have in-depth exploration of stacking, bagging, and boosting. Then we'll go to practical insights, parameter tuning, and how these methods impact variance and bias. Then we'll have tips and tricks like best practices for implementing ensembles efficiently and effectively. And key takeaways as a summary of how and when to apply ensemble techniques. Our focus will be both conceptual and practical, equipping you with the tools to understand, implement, and optimize ensemble methods. Let's take a review of the bias-variance trade-off. We had this topic on the previous lecture, but let us review. So the bias-variance trade-off is critical in machine learning, impacting model generalization. So how it works? Bias, well, a model with high bias makes overly simplistic assumptions, potentially ignoring patterns in the data. This leads to underfitting, where the model performs poorly both on the training and testing sets. For example, a linear method trained on non-linear dataset may show high bias because it cannot capture the data complexity. Variance, well, a model with high variance is sensitive to small fluctuations in the training data, resulting in overfitting. Such models perform well on training data but poorly on new data because they memorized rather than generalized the patterns. And optimal performance requires balancing those errors. Reducing bias often involves adding more complexity, like additional features or deeper trees. Reducing variance typically requires simplification techniques, like regularization or data augmentation. And ensemble methods are crucial in this trade-off. For instance, bagging decreases variance by averaging predictions across models trained on different data samples. Boosting reduces bias by sequentially focusing on correcting errors in training. For tuning bias and variance, consider these approaches. Reducing variance means that use dimensionality reduction to reduce noise, use larger data sets, larger training sets to stabilize learning, and regularization to limit model complexity. And controlling bias, well, adding features helps decrease bias but may increase variance. For models like decision trees, deeper trees often reduce bias but can increase variance unless carefully pruned. Ensemble methods, particularly boosting and bagging, are designed to balance those errors. Boosting iteratively focuses on bias reduction by combining weak learners, often resulting in low bias, high accuracy model. Bagging aggregates models trained on resampled data to reduce variance without increasing bias. And as you can see, this bias-variance trade-off, so we need to find this best point of low bias and low variance at the same time. That will be like ideal model. Let us have a small illustration of the ensemble approaches. The wisdom of the crowd demonstrates how diversity in predictions improves accuracy. For example, in the 1906 experiment by Francis Galton, when 800 people guessed the weight of a cow or an ox, the average guess was remarkably accurate, even though individual guesses varied wildly. In ensemble learning, we replicate this by combining multiple diverse predictions. So each model's weaknesses are offset by the strength of others, and models make independent predictions that are then averaged or weighted, reducing the likelihood of extreme errors. And by the way, this Francis Galton, he invented the Galton board or the Galton box that demonstrates the central limit theorem, and in particular that with the sufficient sample size, the binomial distribution approximates a normal distribution. And among its applications, it provided insights into the regression to the mean. So the primary types of ensemble methods are stacking. Stacking combines various models or Bayes learners, each of which can be of a different type, for example, logistic regression, k-nearest neighbors, and like others, decision trees maybe. A meta-learner is trained on the outputs of these Bayes models to make final predictions. Bagging creates multiple subsets of the training data using bootstrapping, random sampling with replacement. Each subset is used to train an identical model, and predictions are averaged or voted upon. And boostings are trained sequentially one by one, where each model tries to improve on the errors of the previous one. Errors from earlier models are given more weight, pushing the next model to focus on harder cases. Each ensemble method has specific use cases, strengths, and weaknesses based on the data's complexity and the desired model performance. We will start with staking. Staking is a powerful ensemble technique that combines predictions from different types of models on the same dataset. This is an illustration. So we have a dataset, then we have several models predicting something on this dataset. Then we take those predictions, send them to another model that uses the predictions or maybe some other features, but the key is to use those predictions. This model generates new prediction. Let us take a look at the detailed pipeline of staking. The staking pipeline involves two steps. First one is training several models like logistic regression, decision tree, or any other like support vector machines maybe. The key is different models. Then using their predictions as input features for a meta model. And the benefit of this approach is it leverages the strength of multiple algorithms. For example, support vector machine might capture complex boundaries, while a decision tree can benefit by providing nonlinear splits. And the meta model learns how to optimally combine the base model predictions, effectively balancing bias and variance. And as in this pipeline, so we start with the data set, we apply feature engineering, then we use this data set for predictions of several models, then we use the model's predictions for the new prediction. And that's how we use stacking. Of course, there is a high risk of overfitting in staking, and usually staking is not that popular in the production. It often improves performance in complex scenarios where individual models have varied strengths, but in the production is more used like bagging and boosting. And let's talk about bagging and boosting. Bagging has nothing to do with bags. It's the bootstrap aggregating, and it stabilizes high variance models by training them on different random subsets of data. Just take a look at this image. So we start with a data set, then we split it into subsets, then we use each subset to train each individual model. The models here should be of the same type, same tree-based models usually. Then those models make predictions. We use these predictions just to provide an average, and this average or the majority voting as here is used as a final prediction. Let's take a look at the pipeline, the detailed pipeline of bagging. Let us, for example, take a random forest. Each decision tree is trained on a randomly sampled subset, and the predictions from all the trees are averaged or voted upon. So if it's a regression, we have an average. If that's a classification, we have a majority voting. And Bayesian reduces variance. Each model sees different data, so errors made by one model may not be made by others. Averaging multiple predictions reduces the model's sensitivity to the variance of any single tree, improving generalization. And Bayesian works especially well with high variance, low bias models, like decision trees, where combining predictions smooths the fluctuations in individual models. Let's take a look at the boosting. Boosting is an iterative process where each model corrects the errors of the previous one. As on this image, we take the dataset we train model. Then, using the subset of errors from the dataset, we train another model that tries to improve the results of the previous one. And this goes on until we either have the perfect quality or desired quality, or until this is the end of the number of the models that we want to use. Let's take a look at the detailed pipeline. There are a lot of popular boosting algorithms like AdaBoost, Gradient Boosting, Stochastic Gradient Boosting, or XGBoost, Light GBM, CatBoost. And in general, there are three steps. First, the first model is trained on the original data, and the errors are identified. We call those residuals. The second model is trained with a focus on correcting the errors made by the first. And there is a loop, so this continues with each model in the sequence trying to correct errors from the previous models. Boosting reduces bias. By focusing on errors sequentially, it builds a highly accurate model from weak learners. The process usually ends when performance stops improving and a weighted combination of all model predictions is used to the final prediction. Let us break down the comparison of ensemble methods, staking, bagging, and boosting, row by row as presented in our table. This approach will help us understand each method's unique characteristics from purpose to potential drawbacks. So the purpose. Staking is designed to balance both bias and variance by combining diverse model types. This is done by having a meta model learn the best way to weight and blend predictions from various models, capturing strengths of each other. Bagging or bootstrap aggregating is especially aimed at reducing variance. By averaging predictions from multiple models trained on different data subsets, bagging stabilizes results and reduces overfitting in high variance models. Boosting works to reduce bias by correcting errors iteratively. Each model in the sequence focuses on improving areas where the previous models struggled, which makes boosting highly effective for accurate predictions on the complex data. What about model combination? Staking combines predictions from different model types through a meta model. For example, a logistic regression, a decision tree, and a support vector machine might all generate predictions that are then passed to a meta learner, which learns the best way to weight these predictions. In bagging, we use multiple instances of the same model type. This could mean, for instance, training several decision trees, each on a different subset of the data, and then averaging their predictions. By the way, training different instances of the linear regression is not the best idea. Try to figure out on yourself why. Boosting takes a sequential approach where each new model focuses on correcting the mistakes made by the previous model. This allows the ensemble to progressively refine its performance. What about the model dependency? Staking uses independent Bayes models, which are combined only in the meta-model stage. This independence allows staking to handle diverse perspectives from different algorithms. Bagging models are also independent, as each one is trained on a separate subset of the data. The predictions are then aggregated, but the models themselves do not influence one another. In boosting, the models are sequentially dependent. Each model's performance directly impacts the second one. The new model's training is influenced by errors in the previous model, creating a chain of dependency that improves overall performance. However, you should take into account that this increases the risk of overfitting. How the final prediction is made. Staking makes its final prediction through a meta model that aggregates the outputs of the base models. Bagging typically combines predictions through averaging in regression or majority voting in classification, creating a stable and robust final prediction. Boosting combines predictions through a weighted combination where models that handle challenging cases are given more importance, enhancing the model's accuracy on difficult predictions. And what about error handling? So in staking, the meta model learns how to weight the predictions of base models based on their individual strengths and weaknesses, effectively reducing both errors and uncertainty in predictions. Bagging reduces variance by averaging predictions across models trained on different data samples. This averaging process stabilizes predictions, mitigating extreme errors that might occur in individual models. And boosting specifically focuses on difficult cases by assigning more weight to previously misclassified instances. So each model in the sequence becomes progressively better at handling challenging data points. So let's have some examples. So staking can involve models like support vector machines, KNNs, logistic regression as base models, with a linear regression or decision tree as a meta model. Bagging includes well-known examples like random forest, which is a bagged ensemble of decision trees, or even bagged versions of other models like support vector machines. And boosting is represented by algorithms like AdaBoost, Gradient Boosting, XGBoost, and CatBoost, and each of which applies boosting principles with unique optimizations. So what about strengths? Well, staking is highly flexible and powerful because it allows to combine the strengths of diverse models, which is useful for capturing complex data relationships. Bagging is strong in reducing overfitting for high variance models, especially in noisy data environment. Random forests, for instance, are robust against overfitting and can handle a variety of input features. Boosting offers high accuracy and is good at capturing complex patterns. By focusing on challenging cases, boosting effectively reduces bias, making it suitable for complex data with complex relationships. What about the weaknesses? Staking is computationally expensive. It requires significant resources, especially with complex meta models. If the meta model is overly complex, staking can also become prone to overfitting. And bagging generally requires large data sets to be effective, as it depends on creating diverse subsets. Additionally, since each model is the same, bagging doesn't reduce bias. It only works best with high variance models. And boosting, it's prone to overfitting if it's not carefully tuned, particularly if there are too many models or the models are too complex. It is also computationally intensive because each model is trained sequentially, which can significantly increase training time for large data sets. Just to summarize this table, staking is ideal when balancing bias and variance with diverse models. Bagging works well for variance reduction in high variance models, providing stable, generalizable predictions. And boosting is best when accuracy is the priority, especially for data sets requiring nuances to understand. And choosing the right ensemble technique depends on your data, computational resources, and the goal of your analysis. Each method offers unique strengths and potential pitfalls, and mastering them can greatly enhance your model's robustness and accuracy. Let us take a look at several implementations of bagging and boosting, specifically random forest and several types of boosting, and we will take a look at the details and nuances of using those models. Random forest has several key parameters to control. It's the number of estimators. More trees usually mean higher accuracy but longer training time. Max depth, it controls the tree depth and model complexity. Mean samples split and mean samples leave. Higher values make trees less likely to split on small subsets, reducing overfitting. And max features, it limits the features each tree considers at each split, controlling the variance. When it comes to tuning strategy of the random forest, start by setting number of estimators and max depth, then refine with mean sample splits, mean samples leave, and max features. You can also consider like bootstrap and class weights if needed, but only use bootstrapping if other parameters don't improve the results, and class weights improve the performance only for imbalanced datasets. Key parameters for XGBoost include learning rate. Smaller values increase the model's ability to generalize but require more trees. And also, the number of estimators here is the same as in the random forest, it's the number of trees. So max depth is the same. Lower values reduce overfitting but may limit complexity. But in general, the trees in boosting should be smaller than the trees in bagging or like in random forest. Mean child weight sets a minimum for leaf node weight. Higher values prevent overfitting on small datasets. And subsample and call sample by tree, those like limit data and feature subsets per tree, and those parameters control overfitting. When it comes to tuning strategy for boosting, start with number estimators and learning rate, then adjust max depth and subsample, and then you can try scale pose weights for imbalanced data. It's the ratio of negative to positive classes. Basically, it works similar to the class weights in the random forest. The idea is to provide the penalty for misclassifying of different types of instances or different classes of instances. As for the CatBoost, it specializes in handling categorical data. The key parameters here are iterations and learning rate. It control converge speed and capacity, like depth and L2 leaf reg is to limit complexity to prevent overfitting, and bagging temperature, it adds randomness to sampling, reducing overfitting. CatBoost's native handling of categorical values reduces the need for pre-processing, making it ideal for mixed data types. As for the tips for tuning CatBoost, use cross-validation and always use it to evaluate the impact of parameter changes. Keep in mind that CatBoost has a native support for categorical values, and there is no need for extensive pre-processing, and enable GPU for large datasets if you have this possibility. And well, you can even start with CatBoost default values, default parameters, because in most cases they work and they need just minor adjustments. So that's a nice thing to have for CatBoost, obviously. And also for the CatBoost, avoid one-hot encoding. One-hot encoding during preprocessing then will affect the training speed and the results quality for the CatBoost, since it natively supports categorical values. And usually one-hot encoding does not significantly improve the quality of the model, but if it is required, use the parameters of the CatBoost to preprocess it. Let us compare XGBoost, Random Forest, and CatBoost row by row to better understand their unique characteristics and applications. We'll start with the algorithm type. So XGBoost uses gradient boosting with an additive bootstrap framework. This approach builds models sequentially, where each model corrects the errors from the previous one, optimizing overall accuracy. Random forest uses bagging with bootstrap aggregating, using multiple decision trees trained on different data subsets to produce an average prediction, which stabilizes the results. CatBoost, like XGBoost, uses gradient boosting, but it uses ordered boosting, and this approach is optimized for handling categorical data, making it more efficient for data sets with mixed features. And primary use case for all of three models, well, XGBoost is well suited for high accuracy and structured tabular data and is frequently used in data science competitions where precision and control are critical. Random forest is a general purpose model. It works well on structured data, especially with high variance data due to its ability to average across multiple decision trees. CatBoost performs great with tabular data containing categorical features, reducing the need for complex encoding. It is especially valuable when working with the data that contains categorical data naturally. Since I mentioned like the categorical features, XGBoost requires categorical features to be manually encoded, either through label encoding or one-hot encoding. This encoding can add complexity and in high-dimensional datasets slow down the model. Random forest also requires label encoding or one-hot encoding, since it does not natively support categorical data. CatBoost is optimized for categorical data, natively handling categories without the need for explicit encoding, and this feature saves pre-processing time and reduces the risk of introducing encoding-related biases. That is important. What about the training speed? XGBoost performs well on dense, structured data, but can slow down if there are many categorical features due to the need for encoding. Random forest generally has fast training speeds with smaller data sets, but may slow down as the depth of each tree increases. CatBoost is highly optimized for large datasets, especially those with categorical features. It is capable of rapid training on complex datasets thanks to specialized optimizations for categorical data. As for the parameter tuning, XGBoost has a high parameter tuning complexity with many options like learning rate, max depth, and subsamples, and each parameter affects both accuracy and training speed, so careful tuning is required. Random forest has moderate tuning complexity, with fewer core parameters to adjust, such as max depth and number of estimators, making it simpler to configure. CatBoost also has moderate tuning complexity and generally performs well with default parameters. However, if more precision is needed, parameters like learning rate and depth can be fine-tuned. What about the overfitting control? XGBoost relies on parameters like learning rate, max depth, and subsample to prevent overfitting. Regularization terms, lambda and alpha, also play a key role in controlling model complexity. Random forest controls overfitting through max depth to limit the depth of tree and min sample splits and min sample sleeve to control splits, which restrict the model from capturing noise. CatBoost uses parameters like learning rate, depth, and L2 leaf rag to manage overfitting. Additionally, bagging temperature is unique to CatBoost and adds randomness, which can improve generalization. What about the out-of-the-box performance? XGBoost often requires parameter tuning to achieve optimal results, but its high accuracy makes it worth the effort for competitive environments. Random forest performs well out of the box and usually does not require extensive tuning, making it acceptable for general applications. CatBoost generally performs strongly with default settings, often needing minimal tuning, especially when working with large datasets that include categorical features. As for the handling missing values, XGBoost can automatically handle missing values by learning which branches to take in decision trees when data is missing. Random forest does not handle missing values directly, so data imputation or pre-processing is needed to manage any gaps in the data. CatBoost efficiently handles missing values natively, reducing pre-processing requirements and maintaining performance in incomplete datasets. What about the imbalanced data handling? XGBoost offers the scale plus weight parameter, which helps balance class weights, improving performance on imbalanced datasets. Random forest can use class weight parameter in classification tasks to adjust weight. CatBoost has scale post weight, which functions similarly to XGBoost, allowing to handle imbalanced data effectively. What about the support of GPUs? XGBoost supports GPU training, significantly speeding up training on large datasets with high dimensional features. Random forest natively does not support GPU, although there are libs that has this GPU acceleration, and CatBoost fully supports GPU acceleration, especially valuable when training on large datasets with many categorical features. What about the interpretability? Well, in general, interpretability of ensembles is a tricky point, and XGBoost provides moderate interpretability, including feature importance and supports for shape values, which help explain feature impact. Random forest offers similar interpretability with feature importance and shape values, and so goes with CatBoost, feature importance and shape values. What about the best use cases? Well, XGBoost is excellent for structured data with complex relationships and ideal for competitions where high accuracy is essential. Random forest works well for general purpose tasks with high variance as it's robust against overfitting and performs great in structured data applications. And CatBoost is ideal for tabular data with many categorical features, especially suited for production due to its efficiency and minimal pre-processing requirement. And as for the conclusion for this table, so XGBoost performs great in complex structured data scenarios where accuracy is the key. Random forest is go-to model for robust performance, particularly with high variance data. And CatBoost is optimal for categorical heavy data, performing well with default settings and minimal preprocessing. And each model serves a specific purpose and excels under particular conditions. Knowing when and how to use these models can enhance your productivity. In this part, we will go through the code to show how to implement and fine-tune staking, bagging, and boosting, and we will demonstrate real-world scenarios with complex datasets. Hello everybody, and today we are reviewing the ensemble models and exploring different techniques to use ensembles. We will visualize our models and we'll use precision recall curve and other curves to better understand their behavior and metrics. This is a hands-on and we'll utilize a real-world classification dataset to demonstrate the concepts. So let us get started, and we start by installing libs. So yeah, we'll install it. By the way, I'm showing you already processed notebook just in order to save time, because cross-validation takes time and I would like just to avoid it, but you will have this notebook and you will be able to run it and to take a look at it. So what we need? We need XGBoost, CatBoost, libs. We won't be using LightGBM here, but we'll just install it for you to later use. So we install the necessary libs and then we import the libs that we need. We connect the Google Drive in order to use the data set. You will be able to either download it from this link, and I will share the link to the dataset, so you will be able to use your own notebook with the data, with a copy of your dataset. Let us take a look at the dataset, and here we notice that we have binary features like gender, partner dependence, and so on, and some of them categorical. The target is binary, so let's take a look at like more detailed. We have 7,000 entities. And as we can see, some of them are objects and only the minority of them is like float or int. And let's take a look at the uniqueness just to validate which of them are categories. And also let us take a look at the churn variable. This is our target. We can see there is a slight imbalance here, but we won't be using any advanced techniques to deal with imbalance. If you want, you can, but the focus of this notebook is working with ensembles. Let us pre-process the data, since we need to prepare the categorical data and we also need to have numerical data to later impute the data and to scale the data, since one of our models will be logistic regression, or like the type of logistic regression, so we will need to have a scaled features. Yeah, we use simple imputer just for simplicity, and for the categorical data we impute with the mode. We encode categorical columns with one hot encoding, but keep in mind we won't be using these df encoded for CatBoost. We'll use separate dataset for CatBoost. And with this here, yeah, you can see now that we have categorical columns, we have numerical columns. Let us split the data. We'll use the normal splitting, train test split. And again, as I mentioned, we need a scalar. We will use standard scalar here. And now, yes, our categorical and numerical columns. We define the evaluation functions, and our evaluate function will take models and calculate predictions and probabilities and all the metrics, and then also will build some curves. And yeah, those are the functions. You will be able to take a look at them more detailed in details. And yeah, let's take a look at the random forest. We'll review baseline versus tuned performance. We can see that the area under ROC curve is pretty good. However, yeah, keep in mind that the data is slightly imbalanced. But let's take a look at the density plot. And here, looking at the density plot, we can notice that if we separate by 0.5 threshold, then class 0 will have a lot of false negatives, and yeah, that's the intersection. However, yeah, we can take a look at the average precision, the area under curve, and the f-score. By the way, yeah, this is the PR curve, precision recall curve, and average precision is 0.65, which is not bad, not bad. Yeah, we can see that precision here is pretty low, and recall is even lower. Let us tune the model. We'll use different number of trees, different depth of tree, and mean sample split will be also different. And we can take a look at this, and this is the tune model. Well, the performance is slightly better. Let's take a look at the best parameters, best estimator. So it's like max depth 10. Okay, we'll take a look at the best parameters. Best params. Max depth 10, mean sample split 10, number estimators 100. It's almost basic parameters. Let's move to the XGBoost. The same here, like the basic XGBoost. It performs similarly to the base random forest. However, if we take a look at the precision and recall and the density plot for predicted probabilities, the density plot here is a bit different, but if we play around with the threshold, it might behave better for our cases. But the precision recall are better, and the score is a bit better. What if we fine-tune? Yeah, well, fine-tuned is better, obviously better. And yeah, here we have again the improved density plot. And let's notice that this training took 1 second and fine-tuning took 31 seconds. As for the staking classifier, well, it took 31 seconds. Again, the density plot here and the precision is a bit better. What about CatBoost? CatBoost behaves untuned, behaves pretty well, even better than previous models, untuned previous models. We can notice it by those metrics. We don't need this. For the illustration, let's take a look at the performance of the base learners separately. So when they're not in the ensemble, we'll use tree, rich classifier, support vector classifier, and nearest neighbors. So with just basic parameters. We can see here that the performance is worse than for the ensembles, meaning that ensembles do work and ensembles provide a lot of opportunities to improve models. Yeah, let's take a look at the cross-validated results here. Well, accuracy is pretty high for each model. However, if we take a look at the precision is better for staking classifier. And as for the recall is better for XGBoost and CatBoost. F1 score is better for XGBoost and CatBoost. ROC curve and the area under it is better for boosting and CatBoost, XGBoost and CatBoost, and the same goes for the average precision. Based on this, we can choose the best model that fits our needs. Again, I skipped the feature engineering part here, and we only focus on the data and on the ensembles. This comparative analysis provides a picture of each model's consistency and reliability and provides us with the data for making a decision. Just to sum up, we reviewed the models, the ensembles models applied to real dataset, and by leveraging hyperparameter tuning and evaluation metrics, we've gained deeper insights into each model's strengths and areas for improvement. As we can see, untuned CatBoost performs at the level of tuned XGBoost. And this is due to the fact that CatBoost natively supports categorical values, and the majority of data is categorical in this dataset. Ensemble models, when implemented and fine-tuned, can significantly enhance predictive performance, making them invaluable tools in the machine learning toolbox. Please experiment with these techniques in your projects to gain the full potential. Thanks for your attention. Welcome back, and let us continue. And this is the part of tips and tricks. So what can I say? Combine different models. Mix diverse models like decision trees, linear models for better accuracy, and balance model complexity. So use high variance models in bagging and keep learning rate low and boosting to avoid overfitting. Use cross-validation and always evaluate ensembles with cross-validation for robust generalization. And keep in mind the feature importance to understand what is going on and to identify like low impact features or identify overfitting. Try voting and staking. For classification, try majority voting, and in staking, combine different model types for diversity. And watch boosting iterations. Avoid overfitting and boosting by starting with fewer iterations and using cross-validation. And gradually optimize parameters. Adjust one key parameter at a time, starting with number estimators and bagging or boosting. And of course, if you have large data, consider using GPUs, since XGBoost and CatBoost supports GPU training. It speeds up the processing on large datasets. Random forest, on the other hand, provides the parallelization. So if you do not have GPU, you can use random forest and train it in parallel. To sum up our exploration of ensemble models, let us summarize the main points. First one, boost model performance. Ensembles methods like bagging, boosting, and staking enhance model accuracy and stability and generalization. Bagging reduces variance by averaging predictions across similar models. Boosting sequentially improves on errors to reduce bias. Staking combines different model types to leverage diversity. Choose the right method. Select the ensemble technique based on your task. Bagging stabilizes high variance models. Boosting is great with complex data where reducing bias is crucial. And staking is ideal to balance multiple model types and control complexity and overfitting. Ensemble methods can be complex and may overfit, especially boosting. Use cross-validation and carefully tune parameters for generalization. Take a look at the interpretability. Use feature importance scores to evaluate what is going on, and maybe you'll find overfitting or maybe some redundant features that you will just throw out of the datasets. And of course, those will give you some insights on either feature selection or the model itself and the data itself. And yeah, please keep in mind that ensembles are powerful tools with real-world applications. They're widely used in production, and those are great techniques. In summary, ensemble techniques like bagging, boosting, and staking provide flexibility and can outperform single models on complex tasks. When carefully implemented, These methods transform our approach to predictive modeling, delivering reliable and adaptable solutions. Just as a final words, first of all, thank you for your attention. And ensemble techniques are not just tools, they represent the power of collaboration and diversity in solving complex problems. And each model, with its unique strengths and weaknesses, contributes something valuable, just like each one of us brings a unique perspective and talent to a team. In machine learning, like in life, rarely does a single approach work for every challenge. Just as these algorithms combine multiple models to enhance accuracy and robustness, we can achieve great things when we collaborate, learn from each other, and build upon our collective strengths. Thank you for your dedication and curiosity today. And keep exploring, keep questioning, and keep building solutions that make a difference. Stay inspired and remember, great things are often achieved by working together and by working hard.